in simple terms or numerically how or what are these two things, energy spectral density and power spectral density. Then we will go to modulation. In the last class we discussed about modulation. So today also we will continue with modulation. Last class we had the basics. So basics we discussed. Today we will discuss little bit details of modulation. Particularly in this session, we will discuss about double sideband modulation or DSB. DSB has
Namaskar.
namaskar. DSB has two categories. One is called DSB, only DSB. Other is called DSBSC. SC stands for suppressed carrier. So we'll consider the suppressed carrier first. In the next session, we'll consider the DSB, which is also called amplitude modulation, only AM. So with that, let us start. With that background, let us start today's discussion. So we discussed about distortion in the beginning of this course. In the distortion, we said that if there is a communication channel, there are two signals. Suppose XT is a signal and which is being transmitted, and it is transmitted via a medium which is called the channel, and it is received as YT. So if XT and YT, XT is the input signal, that is what we said, YT is the received signal, so message signal is XT, received signal is YT. YT will not be exact replica of XT. When you receive the signal, it will not be exact replica of XT. Usually it will not be exact replica of XT. But that is what is called distortion. Distortion means it is not exact replica of XT. So in that case, if the distortion is more, which means YT deviates considerably from XT, then it is difficult to get back the message contained in the signal that you are receiving, or the information that is being passed will be difficult, it will be lost. So how we first try to know what is distortion, then we saw some of its remedies. Suppose we have a linear channel. If we have a linear channel and the channel has impulse response HT, HT means it is in the time domain. So in the time domain, HT is the impulse response. So if you give an impulse as input to this channel, you will get HT as its response. In the frequency domain, HT will be transferred to frequency domain by Fourier transform. So HT will become now HF, capital HF. Capital HF is the Fourier transform of HT. Now using this HT or HF, what is the relationship between the input signal and the output signal, XT and YT? XT is the input signal. To get YT in the time domain, we take convolution of XT with HT. So YT is equal to HT convolved with XT. So that gives you the time domain picture. Now if you take Fourier transform of both the sides, then YT Fourier transform will be capital YF, HT Fourier transform will be capital HF, XT Fourier transform will be capital XF. Now what happens to the convolution? As you know, convolution in time domain is multiplication in frequency domain, and vice versa. Convolution in frequency domain is multiplication in time domain. So use that principle, take the Fourier transform. So YF will be multiplication of HF into XF. That is why people usually use the transforms, Fourier transforms we use. Instead of doing all these integration etc. in the convolution, go to the Fourier domain. take the algebraic equations, just multiply them. So that is much more easier. Now suppose HF is attenuating both its phase as well as amplitude. So if both are attenuated, then the input signal will be highly distorted. If HF attenuates both the phase or the amplitude of the input signal, amplitude of the input signal is when you multiply absolute of HF with the absolute of XD, that will be uh, attenuated. XD will be attenuated. So output YT amplitude will be is attenuated version. Similarly, output to YT angle is also attenuated version. So in those cases, it will be completely distorted. So these channels where there will be distortion, channels are subject to impairments or defects. Uh, Channels are subject to causing defects in the signal because of different things. One is you can have nonlinear distortion because of the channel, like clipping, this we have seen. Some random noise may be introduced by the channel. These are independent, these noise are independent, and or they are independent of signals. Signals are dependent, but noise are independent. Then interference from other transmitters within the channel. Then self-interference. Self-interference means the same signal can be interfering with itself because of reflections, because of multipath. Multipath means you transmit a signal from point A, it has to go to point B. Now, in between point A and point B, there may be the signal will be transmitted in all directions by the antenna. The signal will be transmitted in all directions. Suppose at point C there is a reflector or there is an obstacle or there is some object at point C. Though the signal goes from point A to point C, then it gets scattered and the scattered part comes to point B. Similarly, the signal from A directly comes to point B. So there are two paths. From A to B is directly A to B, other is A, C, B. So there can be many D, E, other paths also will be there. So these are called multipath. Instead of going through a single path from A to B, it is going through multiple paths and it is getting reflected. So reflections and multiple paths, they result in self-interference. Same signal interferes with itself. Next, back. Now once the channel has introduced some distortion, we have to get rid of the distortion. So for that, what we have to do is first we have to know what is the channel, what is the response of the channel, what is the impulse response of the channel. If we know that, then we can design something called an equalizer. So how what is that equalizer? Equalizer will have a response, frequency response, which is HEQ. So HEQ will be equal to 1 upon HF. Now, so at the end of the channel, when you receive it, at the receiver, you take the equalizer, which response is for transform is 1 upon HF. The channel has HF, and this has the equalizer has 1 upon HF. When you multiply them, you get 1. Therefore, it is equalized. So it is same as x multiplied by HF multiplied by 1 by HF. That is equal to x. So y will be equal to x. So this is theoretical. Exactly you will not get, in practice you will not get exactly 1 by HF, but very approximately equal to 1 by HF. That takes care of everything. So this is what is done here. This slide shows you this. Now suppose the signal, received signal, also includes a noise. So Yt, which is the received signal, is equal to Xt plus Zt. Zt is the noise max, noise or interference, something like that. Then H equalization into Y equalization, that will be Xf plus ZF by HF. So this equalization will actually increase or amplify the noise. So using equalization, this is the problem. It can amplify the noise. If it amplifies the noise, then there is a problem because noise will be more. What you are receiving, there will be more noise. So that will be a problem. So if there is noise, then there are other methods of handling the noise, but equalization does not work properly for noise. Filtering may be a choice. Next. This shows you channel equalization example. HT or the impulse response is equal to ut into exponential minus t. This example we have been seeing from the very beginning. Ut you know what is ut, unit step function ut, and then e to the power minus t, then xt is the square wave, therefore yt is equal to ht convolution with ht. So if you do that, then the impulse response of the channel is ht e to the power minus t, therefore the impulse response will be a exponentially decaying function. So that you can see the first figure, channel impulse response is exponentially decaying. Now, what is the channel frequency response? The channel will receive or will be sensitive to one frequency at the DC. So, you can see there are two curves. The first curve is going from 0, then going from 0 in the y-axis, and in the x-axis when it comes to 0, 0 means the frequency, original frequency or the baseband frequency, DC frequency, you can say the DC frequency. When it comes to the DC frequency, there is a peak, then as it goes away from DC frequency, it again goes to 0. So that is the channel frequency response because it is a square wave. Square wave response is sorry, it is ut. Because of ut, this response you get. Then the other part, which is the inverted S, reflected S, that again is between around 1.5. It remains around 1.5 up to 0 frequency. Then there it suddenly drops to minus 1.5 and remains minus 1.5 at 0 frequency, which means there is a phase change. So there will be a phase change at the DC frequency. That is what is channel frequency response. Now, what is your input signal? Input signal is a square wave. As we have said, it is a square wave. Now you see, if I give this square wave into the channel response, we will get the corrupted signal. So you can see the corrupted signal is from the square wave, you are getting the sawtooth wave. The square wave, if you take its Fourier convolution with ht, that will give you something like a sawtooth wave. So you are getting a sawtooth wave and its amplitude is decreasing, so attenuated getting attenuated. And next. Now, to equalize this, we have to use a filter. So, filter will be used as an equalizer, whose transfer function will be 1 by j omega, which is 1 plus, whose transfer function will be 1 plus j omega, which is 1 plus j 2 pi f. Omega is equal to 2 pi f. So, that type of filter usually approximates a differentiator. So if you have that transfer function, amplitude of 1 plus j 2 pi f is shown on the left hand side top. The angle of that is shown on the right hand side. Now, what do you get from this? What you can see, particularly see the angle response. It goes from 1.5 to goes from minus 1.5 to 1.5 at 0. So at the desired frequency, it goes from minus 1.5 to zero point 0.5. So there is a phase change uh, from minus 1.5 to oh, 1.5. Earlier, before the this, because of the channel distortion was 1.5 to minus 1.5. So the phase change is reversed. Similarly, look at the amplitude. So there you have seen the amplitude. Now this amplitude is exactly opposite of that. So that also will be compensated. So the impulse response of the equalization filter will be like the one at the bottom left. So and if you pass the signal through this, the equalized signal you can see on the right hand side. So it is almost same as the square wave, not exactly because at the edge you can see some peaks or ringing that remains because of Fourier transform. So that will be there, but that we can always handle with other circuits. So you get almost a square wave as the equalized signal. So you gave input as equalized signal, you get output. You get gave square wave as input signal, and the equalized signal is also a square wave. Next. Now, so that is about distortion. Now let me come back to signal energy and energy spectral density. This we discussed last class. So let me first discuss this, then we'll go to power spectral density. Now you know you have read Fourier transform. In the Fourier transform, you have read a theorem which is called Parseval's theorem. So, Parseval's theorem for an energy signal GT, GT is the energy signal. Suppose you take an energy signal GT. Then, based on Parseval's theorem, you say EG, which is the energy content in the time domain or frequency domain, total energy in the signal EG, that will be equal to integration minus infinity to infinity absolute gt square dt in the time domain. In the frequency domain, it will be integration minus infinity to infinity absolute gf square df. So, in the time domain or in the frequency domain, you will get the same total amount of energy based on the Parseval's theorem, using the Parseval's theorem. Now, there is something called essential bandwidth. Once you know what is the energy content or energy of a signal, then you want to transmit that signal. So over which frequency will send the signal? All the frequencies that is covered by the signal, or you can transmit it over a certain range. For example, audio signal is from 20 to 20 kilohertz. Most of the signal is at the lower frequency. High frequency content is very small. So you can neglect that. So essentially, signal is contained in the lower frequency band, audio signal. Similarly, when you look at any other signal, you have to find out what is the essential bandwidth. So essential bandwidth is the range of frequency or is the band of frequency where most of the energy of the signal lies. So that contains most of the energy of the signal. The definition of most, when you say most, what do you understand? Usually, it will depend on the application. For example, you can say it is 90% of the signal energy. So if it is 90%, use GF as a low pass filter or low pass signal. EB is the energy from minus B to B, where it is EB means it is in the essential band, not EG, it is in the essential band. Then EB will be integration minus B to B. This is the band over which you are finding the energy. So it will be minus B to B integration absolute GF square dF. That you have to integrate. Original signal is EG is equal to integration minus infinity to infinity absolute GF square dF. So integration limit has changed, and you have found out EB and EG. Now essential bandwidth is 90% means ratio of EB to EG should be 0.9. So that is what is essential bandwidth. You can change it to 95%, so it will be 0.95. 85% it will be 0.85, etc. Next. So there are, this is an example. This shows you the spectrum, energy spectrum. The figure shows you the energy spectrum. In the energy spectrum, F goes from minus infinity to infinity, and GF is plotted. 10% of energy is in this shaded region. That is where 10% of energy lies. Rest lies within the band of minus B to B. So that is where 90% of energy lies. So this is an example or illustration. Other definitions are 95% or 99%, half amplitude width, half power width, 50% energy, etc. Next. Now we come to the autocorrelation and energy spectral density. Autocorrelation of a signal, as we defined it, it is the correlation of the signal with its time delayed version. So psi gt is the autocorrelation of the signal gt. So if size it is the autocorrelation function, then this will be minus infinity to infinity. You are finding the autocorrelation. So integration minus infinity to infinity z tau into g star t plus tau d tau. So integrate over d tau. This will be the right hand side will be a function of t because you are integrating it over beta tau. So since it is integrated over tau, it will be a function of t. So this gives you the signal autocorrelation. Now, based on this, I am giving you a homework that find the Fourier transform of psi zt and show that psi zt is equal to absolute gf square that you can write as psi f. Absolute gf square you write it as psi f, and as a homework you show that the Fourier transform of psi zt is equal to absolute gf square. Do this as a homework. You will learn many things about the Fourier transform from this. Now this is called the energy spectral density or the ESD of the signal. Okay, so this is called the energy spectral density. Once you find out psi gt and take its Fourier transform, that Fourier transform, so find the autocorrelation of the signal, take its Fourier transform, that gives you energy spectral density or ESD. What it gives physically it implies the energy of the signal is located in which band. So where the energy of the signal is located is obtained from ESD or energy spectral density. So that is shown in the following figure. In the figure you can see uh, GF absolute GF square is plotted against F. Take a very small band of F which is DF. So there the absolute value will be absolute GF square DF. So that much only will be there. Then you can find out from this EZ will be equal to minus infinity to infinity GF absolute square DF, that you can write as minus infinity to infinity GF absolute square is equal to psi f, so that you can write as minus infinity to infinity integration of psi f over df. Next. These are some examples. Let us see one example here. Now let us say gt is a gate function. So gt is equal to pi to t is the gate function. And since gt is equal to pi to t, you can plot it like the top figure. So around the 0, you have a square wave, not the square wave. You have a square function. So or a gate. Around 0, you have a gate symmetrically placed around 0. That is the gate function. 2t means from minus t to plus 2t. That is why we have taken 2t. So from 0, minus t on the left hand side, plus t on the right hand side. That is what it is. Now its autocorrelation function psi t for zt will be psi zt. Now to find out the autocorrelation, follow the principle that we just discussed. Uh, so then you will get psi zt, that will be from Fourier analysis you can get this. So you take this gate function, do a Fourier transform, that will give you a delta function. Sorry, yeah, that will give you a triangular function. So gate function taking Fourier transform gives you a triangular function. So that will be half delta t. So triangular function. So you get a triangular function there. Now, energy spectral density, once you know what is psi t, then from the triangular function you can find out what is energy density, energy spectral density. So that will be the one which is shown below. Because triangular, that it's once you integrate that, the integration will give you psi f is equal to 1 by 4 sink square pi by 2 f. So 1 by 4 sink square pi by 2 f is the bottom picture. So energy spectral density you can get in this manner from GT. So this is one example. Next. Now we'll come to autocorrelation and power spectral density. Energy spectral density we discussed. I gave you one example. Now we'll come to power spectral density. Now for power signals, unlike energy signals, in power signals, what we do is we normalize the ESD by its duration. Energy spectral density is normalized by the duration of ESD for how much, what is the time period for which ESD will exist, normalized over that. So that will produce the power spectral density of PSD. So normalizing ESD by duration produces the power spectral density of PSD. You know, autocorrelation for a power signal GT, that is defined as when you are using duration, limit t goes to infinity 1 by t is the duration. So instead of saying minus infinity to infinity, I'll say it like this. Limit t goes to infinity 1 upon t, integration minus t by 2 to t by 2. This is minus t by 2, not t by 2. The bottom one is minus t by 2. So integration minus t by 2 to t by 2, g tau, g star t plus tau d tau. That is the autocorrelation. Its Fourier transform function will be, if you take its Fourier transform, this will be limit t goes to infinity, capital T of the period goes to infinity, 1 upon t psi z t f. That is called SGF, and SGF is called the power spectral density. It shows you the frequency distribution of the power of the signal. How the power of the signal is distributed in the frequency. Now this is an example. In this example, we will see GT as a binary sequence of rectangular pulses. So GT is G1T get function of 2T, and it is a sequence. It is not one function. So it is periodic. Energy signal is always aperiodic. Power spectrum is always periodic. So here it is 2 pi, pi to t. So from that you can say Gt is equal to an G1t minus n summation over n. So that is what is Gt, how you represent Gt, and G1t is the get function. Now for small displacement, slightly displacing, the autocorrelation will look like this, the following one. So how do you do the autocorrelation? Displace it over its displaced value. So gradually you shift it over there, so it looks like this. Now, if you normalize this by the interval t, this will be the same for a signal, say for a single pulse. Next. Now, suppose you have large displacement. In the large displacement, there will be overlaps which are like to be plus minus 1. Now, if there will be overlaps of plus minus 1, they will cancel. So, this will go to 0 as t gets larger. Then the autocorrelation will be a triangular function, because those will be 0. So only one gate function remains around 0, others will be cancelled out. So they will go to 0. So t, as t gets larger, everything goes to 0, excluding the one at the t is equal to 0. So that will remain. Its function is, it becomes a, its autocorrelation is triangular function. Power spectral density is same as the previous one. So power spectral density will be like the energy spectral density in this case. Next. Now, We discussed in the last class what is baseband communication. Baseband, what is baseband? Baseband or message signal or modulating signal, those things we discussed in the last class. Baseband is the frequency band of the original signal. So if you have the original signal which contains information, its frequency band is called the baseband. For telephones, baseband is 300 to 3700 Hz. High fidelity audio, hi-fi audio, it is 0 to 20 kilohertz. Television, TV, for TV, it is 0 to 4.3 megahertz. Ethernet that we are using uh, uh, in the internet connections, we are using Ethernet cables. So Ethernet, where it is, if it is 10 Mbps speed Ethernet, it is 0 to 20 megahertz. So they usually baseband communication, they require wires. Mostly they require wires. You cannot have multiple baseband signals sharing a single channel unless you have time division multiplexing or TDM. Time division multiplexing means suppose there are two signals. There can be n signals. I am taking example of two signals. If you have two signals, signal 1 you will transmit at time t is equal to 1. Then signal 2 you will transmit at time t is equal to 2. Then at time t is equal to 3 again you will transmit a sample of signal 1. Time t is equal to 4 you will transmit sample of signal 2. This way you will do it. That is what is called multiplexing, time division multiplexing. Multiplex the signals in the time. Next. Now, what is carrier communication? This also we discussed in the last class. What is carrier? Carrier is the signal that carries the baseband signal. So, carrier communication uses modulation to shift the spectrum of the signal. This we discussed in the last class. Wireless communication, they require frequencies which are higher than the baseband signals. Multiple signals can be sent at the same time, so you don't require a TDM. So at the same time, you can send multiple signals using different frequencies. For example, you can use frequency division multiplexing. So at different frequency, you can send different signals. In carrier communication, the signal modulates a sinusoidal carrier. Signal means the baseband signal. So the baseband signal or the message signal that modulates the sinusoidal carrier. Modulation is what you have understood in the last class. We discussed what is modulation, changing the characteristics of the carrier signal is modulation. So the signal will modify the amplitude or frequency or phase. These are the three characteristics of the carrier. Those can be modified. Now suppose we are considering a signal st. St is equal to at cos omega ct plus phi t. So at is the amplitude of the signal. This is the carrier signal. Omega c is the uh, frequency, carrier frequency. Fc is the carrier frequency. Phi t is the phase. So in amplitude modulation, at will be proportional to nt. Frequency modulation, Fc will be proportional to nt. Phase modulation, Phi t will be proportional to nt. Frequency and phase modulations are called exponential modulations or angle modulations. We'll discuss them later. Next. Now we come to double sideband suppressed carrier modulation. This part is important, very important from your examination point of view. This double DSBSC, seeing this, is a complicated way of saying multiply by a cosine or multiply by a sine. So multiply by a sinusoidal signal. So you have your carrier signal, multiply that with a sinusoidal signal. That is what DSBSC is. So you have a message or baseband signal and a cosine, which is cos omega ct at the frequency Fc, carrier frequency Fc. Then the modulated signal will be mt into cos 2 pi fct. Now if you take mt into cos 2 pi fct and take its Fourier transform, in the Fourier domain, this multiplied signal will be 1 by 2 into m of f plus fc plus m of f minus fc. What is capital N? Capital N is the Fourier transform of small n. So MT is the a message signal. Its Fourier transform is capital MT, capital MF. So if you multiply this with cos, then you will get 1 by 2 mf plus fc plus mf minus fc. Now you know, if I do a block diagram, in the block diagram, if I want to show you, you will have a multiplier or a mixture or multiplier are same thing. So the circle with a cross within it is signifies a multiplier or a mixture. So there are two inputs to this circle. One is empty, other is cos 2 pi fct, and the output of the mixture is empty cos 2 pi fct. So this is the block diagram of generating DSBSC. In the next page, we will see example of the signal and its spectrum. Next. So DSBSC, now look at this. MT is some arbitrary function, some arbitrary signal. So we have the top left one is MT, some arbitrary signal. Its Fourier transform is shown on the right hand side. Top right hand side, it gives its Fourier transform. Bottom is the modulated signal. So you have multiplied MT with cos 2 pi fct. So that signal is shown in the bottom, modulated signal. So we have three signals: baseband signal or message signal, carrier signal, and modulated signal. So when carrier signal is modified by the baseband signal, the resultant is called the modulated signal. So we have the modulated signal. You can see the modulated signal at the bottom left. That is the modulated signal. Now, what you can see here is in the, if you look at this signal, modulated signal, look at it closely. The black core, black sinusoidal core, has a higher frequency compared to the empty. So carrier frequency is higher than empty. That is point 0.1 that you see. Then the amplitude of this black core varies. With time, the amplitude is varying, and it is varying according to MT. So if you draw a dashed line through the peaks of the carrier signal or the modulated signal, if you draw the line through the peaks of the modulated signal, then what you can see is the dashed line resembles the MT. So, which means that the amplitude is varying in the modulated signal, the amplitude is varying according to the message signal. Now, if I take its Fourier transform, what will happen? MF is around the baseband or around f is equal to 0. Now, with the Fourier transform, MF goes to uh, f plus minus fc. Fc is the frequency of the carrier signal. So when you take the Fourier transform of mt with cos 2 pi fct, mf is the Fourier transform of mt, then this mf will shift to the left side to the and to the right side, and its amplitude will be half. So you can see the in the Fourier domain, you can see how what is the Fourier domain. Half m of f plus fc is on the left hand side above minus fc, and half a m of f minus c is placed around fc. So the signal, message signal shifts to fc and minus fc, plus fc and minus fc, and the total energy has to remain constant, total power has to remain constant. That is shown by half. So half, half. So if you add them, that will become 1 m. Next. Now we can think of modulation as a frequency domain convolution. So it has convolved in the frequency domain. Modulation is nothing but a frequency domain convolution. What we have done here is MF, look at the figure, MF is the frequency domain representation of MT. Then we have cos 2 pi fc. Cos 2 pi fc, its frequency domain is two impulses at plus minus fc. So those will be two impulses. Amplitude will be 1 by 2. So 1 by 2 impulse is delta. So 1 by 2 delta f plus fc. That is Fourier transform of cos 2 pi fc. So 1 by 2 delta f plus minus fc, those are at minus fc and plus fc. Now if you convolve these two, by convolution what will happen? The mf will shift to minus fc and to plus fc. Amplitude will be half. So that is what is shown here. Next. Now if you want to demodulate this signal, so what we have got in the modulated signal, what we have got? We have got message signal at f plus fc and f minus fc. So minus fc and plus fc, that is where the message signal is placed. Now what we have to do is we have to get them back to around the 0. So f is equal to 0, that is where the original signal was there. So we have to get them back to those positions. What we'll do, convolve with again, and again convolve this with the cosine. So cosine is minus fc plus fc. When you convolve that with the top signal, then what will happen? Look at the plus fc part. First, let us look at the plus fc part. So plus fc, when it is convolved with at plus fc, you have m f minus fc. That is from the for the message signal. For the carrier signal, we uh, have delta f minus fc at plus fc. When you convolve them, what will happen? This half m of f minus fc will be shifted to two sides and that will become half. So to the left it will shift by an amount of fc, to the right it will shift by an amount of fc. So to the left it will come to the by an amount of fc, which means it will come to around the 0, and to the right it will go by an amount of fc, so it will go to 2fc. So at 2fc you will see 1 by 4 f minus 2fc. Same thing for the left signal. So half of this will go to the minus 2fc, half of it will come to the 0. So at the 0, 1 by 4 uh, will be added. The two 1 by 4 signals will be added. That will give you 1 by 2 MFFC. So around 0, use a low pass filter. So if you use a low pass filter, high frequency will be filtered out. What you will get is the original signal, which is between the or which is around the baseband. So you recover the original baseband signal using a low pass filter. Next. So this is a mathematical representation of the same thing. So what we are doing is we are first modulating the signal. So in the modulated signal spectrum is uh, half m of f plus c plus half m of f minus c. Now multiply this signal by cos 2 pi f c. So what is effectively what you are doing? First you are getting f of mt into cos 2 pi fct. You are multiplying that with again cos 2 pi fct. So the in the demodulation case you are getting uh, mt of cos square 2 pi fct. So take the Fourier transform of mt into cos square 2 pi fct for the convolution operation. So that will be equal to 1 by 2 m plus fc plus 1 by 2 m minus fc convolved with half delta f plus fc plus half delta f minus fc. And so half, if you take, there are two half terms, so that will give you 1 by 4 leaving m of f plus minus c and a delta of f plus minus c. So that will ultimately lead to the convolution will ultimately lead to 1 by 4 m of f plus 2 delta c plus half mf plus 1 by 4 m of f minus 2c. Now you using low pass filtering, we will get back the original signal mf. So we recover the signal. So this is the mathematical explanation using the Fourier transform. Next. Now this is a block diagram for the entire system. So for the entire system, what we have done, we took the MT, then took a multiplier. In the multiplier, we multiplied MT with cos 2 pi FCT, which is the transmitter. So at the transmitter end, we did this multiplication, then we transmitted it through one antenna. That propagates and is received So the multiplication gives you mt into cos 2 pi fct, which is propagating, and it is received at the antenna at the receiver. So receiver antenna you get mt cos 2 pi fct. Multiply again that with cos 2 pi fct at the receiver end. Then use a low pass filter HF. So once you use a low pass filter, use an active low pass filter, so it will be amplified. So you are receiving half of MF. So amplify it by 2 times, so that will give you 80. So once it goes through, you will get 2T. So this receiver is called a synchronous receiver, which means that the transmitter and receiver, they have to be in phase. By synchronizing the receiver requires a more complex system, because unless the system they are in completely synchronized, then there will be problem. Why problem will be there? If they are not synchronized in the receiver, cos 2 pi fct can be cos pi 2, so cos 2 pi fct plus theta. So if you multiply cos 2 pi fct plus theta with mt cos 2 pi fct, you will not get back mt. So you require theta to be 0. So if there is a theta in the transmitter, that theta has to be there in the receiver. So in practice, practically, there will be propagation delay, which is also unknown. You don't know how much delay will be there in the propagation. And this delay is time varying. And the transmitter and receiver phase, they can drift because of this delay with respect to each other, and there will be. So you require synchronous detection, and this is the problem with DSB. Synchronous detection is required. Next. Now let us see how to synchronize this detection, how you are going to synchronize this. Suppose where the transmitter has a phase of minus pi by 2, so that the modulated signal is mt cos omega ct minus pi by 2, so that you can write as mt sine omega ct. Spectrum will be what? Sine, if you have sine, then it will be j by 2 m f plus c minus j by 2 m f minus c. So this is the Fourier transform of the signal which has a phase of minus pi by 2. Now if you demodulate this with cosine, the result will be something like this. So sine spectrum you can see at the top. Then for the cosine spectrum you can see which is at the middle one. And those spectrums, once you multiply or do the convolution, they will be the bottom one. What happens to the signal at the 0? At the 0, you can see the sine spectrum as minus fc is positive, plus fc is negative. So those spectrums are 0. They translate to 0, but they cancel out. One is positive, other is negative. So they will cancel out. You will not receive anything around the baseband. So 0 is baseband. So around the baseband, you will not receive any signal. Signals will be at plus minus 2 fc. So those are of no use. Next. Now what will be the solution in the demodulation? So this solution comes from the complex exponential. Exponential j omega ct. Its Fourier transform is delta f minus fc. So take that. So if you take that, then we have the top one convolved with the here, delta f minus fc. Top one is for sine. Then remember that. So top one is for sine. So the middle one is now for exponential. So you have delta f minus fc. Now since we have only at fc, the delta function is at only fc, not at minus fc. Therefore, when you do the convolution, things will uh, come to baseband 0, around 0. So the spectrum will be shifted to baseband 0. So there you use a low pass filter and get back the original signal. So this method will work for any arbitrary phase shift also, not only for 90 degree, for any other arbitrary phase shift. This will work. Next. So suppose the input has a phase shift of minus theta instead of minus pi. So the spectrum of the carrier will be Fourier transform of cos omega ct minus theta. So cos omega ct minus theta, its Fourier transform, that is cos omega ct minus theta is cos omega ct cos theta plus sin omega ct sin theta. Take the Fourier transform, that will be half exponential j theta delta f plus fc plus exponential minus j theta delta f minus fc. So the spectrum of the modulated signal will be now uh, Fourier transform of, if you take this Fourier transform of nt cos omega ct minus theta, that will be exponential j theta by 2 into f at f plus c f plus fc plus exponential minus j theta by 2 into m of f minus fc. So next, so that will demodulate. So you can see the top one is for the message signal with a phase shift of theta. So top is the message signal with phase shift of theta. Middle one, that is convolved with the middle one, which is a delta f minus fc. Finally you get, as in the previous case, here also you get uh, the baseband signal back using low pass filter. So low pass filter will extract e to the power j theta by 2 mj omega, that corresponds to the complex signal. Okay, next. Now the system looks like this: nt multiplied by cos omega ct minus theta, and that gives you the transmitter, but is propagating mt into cos omega ct minus theta. That is what is received at the receiver. At the receiver, you are multiplying it with the signal exponential j omega ct. Then you are using a low pass filter that gives you e to the power j theta mt. So this is called a quadrature receiver, which is commonly used in radar, sonar, ultrasound, MRI. MT is a simple pulse, and interesting information is actually in theta in these applications, such as Doppler shift for weather radar. This is also common in communication systems. You can buy a digital chip which implements the quadrature receiver in your cell phone. Cost of is that the receiver has to be implemented for complex signals. This is done by way you do it, that is by keeping track of the two real signals, the real part and imaginary parts, that is in phase and quadrature channels. So I and Q channels, in phase and quadrature channels. Next. So with that, we come to the end of our discussion for this session. Once I complete the modulation, then we'll have the quiz. So I thought there is no point in taking the quiz at this point. So once we complete modulation, at least amplitude modulation completely, then we'll have the quiz. So we'll stop here. We'll come back in the afternoon at 2 o'clock. So, and there we will discuss about SSB, start with amplitude modulated signal. Then we'll come to SSB signal.